Hi everybody, it's Mr. Ray here. Next lesson in calculus. This is our distance learning lesson number 9 in the previous way of organizing it. This would be Unit 5, Lesson 7. So that's what the notes will say in the homework solutions. So this is our last lesson in the unit about introducing calculus. I think the next unit you'll find a little more interesting. We had a lot of the stuff in this unit is basically formal formal calculations, and in the next unit we'll be looking at derivatives. You'll be able to find derivatives a lot quicker than finding the slope of tangents, okay? But you will see that they are exactly the same thing. Okay, so this is wrapping up the introduction to calculus. So this lesson is called continuity, which is basically you determine whether a function is continuous or not at a specific point in the function, a specific value of x. So we've got our definition of limit. Limit has a lot to do with continuity, but it's not the same. Here's the formal definition. So if it's not continuous, it's discontinuous. It's black or white on this. Okay, there's no gray in between. So here's the formal definition. There's a much better one below. A function is continuous if it can be drawn without picking up the pencil. So that's a really good way of determining. Can you go through that point without picking up your pencil and moving it somewhere else or skipping over? Otherwise, if it's not continuous, it's discontinuous. So function f of x is continuous if the limit of f of x as x approaches a from either direction is equal. So that's basically saying there is a limit as x approaches a. That limit exists, but there's another condition that has to be true as well, and that has to do with the actual value of the function at that point a. So if we look at, I kind of like this definition because you know what you have to get and compare. Also the one about the pencil is a good quick way of determining. By looking at the graph, you can tell right away, did I have to pick up the pencil at that point and move it somewhere? If I didn't have to pick up the pencil, it's continuous. Otherwise, it's discontinuous. So the formal, this is a nice definition here. Function f is continuous at x equals a if f of a is defined. So basically, there is a value of the function at that point, at that value of a. So it is defined. The second condition is that the limit of f of x as x approaches a exists. So that's what we just did in the last lesson. And then the third one basically puts these two together, that limit and the value of the function at that same point have to be equal to each other. Okay, so it's basically taking, does the limit exist at that point? Does the function exist at that point? And are the two values, the limit and the f of a, are they the same value? Okay. Now I'm going to show you some examples of this just below, but I'll just talk about this first. A function that is not continuous has some type of break in the graph. Okay, so we've got three different conditions or types of breaks. We've got a hole, a jump, or a vertical asymptote. So you probably remember a hole from advanced functions, and we've also seen them in this unit as well. Vertical asymptote, you can see that if you're trying to determine if a function is continuous at a vertical asymptote, you can easily see it's not, because you'd have to pick up your pencil. Actually, for an asymptote, you could never pick up your pencil because you're never going to get to that point. The next part, polynomial functions are continuous for all real numbers. So that was also true of the limit for any real number. At f of any real number, the limit exists and it's always continuous. Okay, a rational function where you have two polynomial functions dividing is continuous at x is equal to a, providing that the value of g of a is not 0. Obviously, divide by 0 would throw a wrench into that. Rational function in simplified form has a discontinuity at the zeros of the denominator. Okay, so that's if you just basically if you factor the denominator of a rational function, you'll have either a whole or a vertical asymptote at where those factors equal 0. When the one-sided limits are not equal to each other, then the limit at this point does not exist and the function is not continuous at this point. So here's a nice little breakdown graphically. Let me try to zoom in a bit. Okay, so we've got, this is a function that's continuous at all values of the domain. You can easily see I can draw this without picking up my pencil. This is not a polynomial function, but sort of a piecewise function, but you can see that if you were to take the limit at any point, as you're approaching that value of x from both sides, it's the same limit, and the value of the function at that point is the same as the limit. Okay. The other three examples here are when it's discontinuous. So here we have a whole. The formal math name for a whole is point discontinuity. It's hard to say. So this is where a lot of times it's a straight line, but it could be some other curve, like a parabola. But you've got a whole there. The function's basically not defined at x equals 1. So it's discontinuous at that point because there's no value of the function at that point. The limit for that at x equals 1 does exist, but since the value of the function at that x equals 1 doesn't exist, then it's discontinuous. Okay, here you have something you've seen before when we did some piecewise functions. You've got a piecewise function here and over here, and you can see the limit at x equals 1 from the left side and the right side as x approaches 1 from the negative side or 1 from the positive side. It's not the same one-sided limit, so therefore the limit doesn't exist, and you don't even have to check the value of f of a here, f of 1. It doesn't matter because the limit doesn't exist. Okay, here's where you have your infinite discontinuity. This is basically when you have a vertical asymptote. So in this case, the limit actually does exist. If you're taking the limit of for f of 1 as you're approaching 1 from the negative side and 1 from the positive side, both of those limits are positive infinity. So the limit exists at x equals 1, but the function is not defined at x equals 1, so therefore it's not continuous. It's discontinuous. So those are the three types of examples of when it's discontinuous. Okay. All right. So this should be a fairly quick lesson. Zoom back out. Okay. So here we've got another a function defined. It's a piecewise function. Basically, there's a kind of a break at x equals -1, and it's x squared minus 3 on the left side, or to the negative side of -1, and also right at -1 we use that formula, and to the right, or when x is above -1, we use x minus 1. So these piecewise functions are always good if you do a rough sketch. So the key thing here is at x equals -1, that's where strange things can happen. That's where the function breaks apart. We want to see if it's continuous or not, just because whether it's if it's piecewise doesn't mean it's not continuous. It could very well be, but we have to check it. So what we do is we're going to take the value, the best way to say this, so at f of -1 for the top piece, which is actually where you would plug in -1 for the function anyways, if you plug in -1 here, you get -1 squared, which is 1. 1 minus 3 is -2. So what I can say here is, if I'm going to draw this top function, let's do some scale here, so that's -2. So that point there, and I can make it a closed circle because we're using that branch for when x equals -1 as well, and everything below. So basically to the left of this will be the function x squared minus 3. And x squared minus 3 is a parabola that basically, it's got its vertex down here and it goes back up, but I'm just going to draw this part. So it doesn't have to be perfect, but it is a part of a parabola. If you wanted to, you could, just do a dotted version over here, but we're not using that part because this is only valid when x is less than -1 or equal to it. Okay, then we're going to do the same thing for the lower branch or the right branch, f. Now this isn't totally true. If I plug the value -1, I should just say x equals -1, not f. So when x is equal to -1 for the lower branch, it's -1 minus 2. That's also equal to -2. So you can see at that point where the function gets split, the value is the same for both piecewise parts of the function. Now this is a linear function, and it's going to have a y-intercept of -1 and a slope of 1. So this would be like a straight line here, and on this side it would just keep going, but we're not using that part. So this darker curve and line, that would be our function f. Okay. Now what we do, so they only asked us to graph in the first part. In the second part, they want us to determine the limit. Nice and easy to do with the graph. So this first limit is well, I guess we could do both. So we could look at the limit as x approaches -1 from the negative side of f of x. So that's basically as we're coming down here from the negative side, as we're approaching x equals -1, the limit is -2. Okay, and then if we do the same thing from the right side, so the limit as x approaches -1 from the positive side of f of x, you can see it's going to be the same thing as we approach from the right side and get to x equals -1. The function is approaching -2 also. So the fact that these two match, that tells us that the overall limit as x approaches -1 of f of x is equal to -2. So that's our answer. So you could just look at the graph and say, but it's a little more cleaner mathematically if you show that it's the same from both sides. Okay. Obviously, if it wasn't the same, that'd be very important to show they're different. Therefore, the limit doesn't exist. Okay. Now, the value f of -1, well, that came from this branch here when x is less than or equal to -1. So when we plug -1 in there, we got -2. Okay, and then it says, is f continuous at x equals -1? And since this limit, this value of the function is equal to the limit as the function approaches x equals -1 from both sides, since these are the same value, then it is continuous. So therefore, yes, since the limit as x approaches -1 of f of x is equal to f of -1. Okay, now that visual of the picture, which we were doing these types of pictures for piecewise functions to determine if a function had a limit or the limit existed, and if it did, what was it. We used these same pictures, but now we're also bringing in now what is the value of this function at that value of x. So now that has to be the same. We did have some examples where maybe the two sides had the same value for its limits, but maybe the actual value of the function was somewhere else for some reason. And in that case, if now we're looking at continuous or not, that would not be continuous. The fact that the value of the function is the same as the limit means that the limit does, sorry, the function is continuous at that point. Okay, get another question at the bottom of the page. Okay, test the continuity of each of the following functions. So this is actually the first of 5 different functions. And for all of them, we're going to look at x equals 2 and decide whether the function is continuous at that value x equals 2. So hopefully by the time we get a couple of examples in, this should seem pretty obvious. So we're going to do 2 things. We're going to look at, so in this case, we want to check the value of f of 2. So we plug that in, we get 2 cubed minus 2. 8 minus 2 is 6. Okay, and the limit as x approaches 2 of f of x. Now, in this case, this is a polynomial function. So, you know, we could have probably just said, well, this is a polynomial function, therefore it's continuous for all values of x. But this is showing the more formal way of proving it. Okay. Now, if you looked at the limit, if you actually drew the graph, x cubed minus x, you would see, you can basically, when if you plug the value into each part, you can see that that's going to be the same calculations. It's going to be 2 cubed minus 2, which is 6 again. If you were to graph this function, you could definitely see it's, you know, it's continuous. You don't have to lift your pencil. The limit at x equals 2 is the same as f of 2. These two match, and therefore f of x is continuous at x equals 2. Okay? So we're going to do other functions, not just polynomials, to make it a little more interesting. So we've got a couple of rational functions, two or three rational functions here. So in this case, we've got a quadratic over a linear, and you could probably guess what's going to happen here. You can actually factor the top. Let's do it down here. That's going to be x plus 1, x minus 2 over x minus 2. All right, those two cancel out, and we're just left with g of x is equal to x plus 1. And because we canceled those two factors out, that tells us there's a hole at x equals 2. Okay, so the fact that there's a hole there, if we were checking, since we are checking for whether it's continuous or not at x equals 2, obviously that's one of the cases where it's discontinuous. But let's do it the formal way. So if the first thing we're going to do, the function's g, so g of 2, we plug that in, we get, what would that be, 4 minus 2, that would actually be 0 over 0. So it's not defined. Even if you, like, you can't just plug it into x plus 1 and get 1, because the fact that you cancel those factors means there's a hole there. That gets lost. Okay, so this is not defined. So the value at g of 2 is not defined. So we don't even have to check if the limit exists at g equals as x approaches 2 from both sides. It doesn't matter if we're just looking to see if it's continuous. This tells us right away that it's not continuous because there's a hole there. Now, if they had asked, for any other value of x other than 2, it would be continuous. So we get the value for that point, say g of 1, and then we'd show its, the limit from both sides is also 1, therefore it would be continuous. But this is the one case where the one value of x where it would not be continuous at x equals 2, and that's because there's a hole there. Remember, there's 3 reasons for it to not be continuous, so you can impress teachers by saying the reason as well. So this is because there's a hole here. Now, here's another, basically have the exact same situation, same function, but we just call it something different, h. This time, so I guess, we could simplify that to x plus 1, because we cancel the x minus 2's. Now, this is very important because it's basically saying the function h of x is this when x is not 2, but when x is 2, h of 2 is 3. So it's basically saying we're going to patch that hole by saying the value of the function at the hole is going to be 3. Okay, so that's kind of a enhancement to this function. We just added this part to the end to patch the hole. So at that point here, that basically says there's no longer any hole because the hole has been patched. Now we still have to make sure that that value matches that value of the function. So we know that h of 2 is 3 because they just told us that, and we could say the limit of h of x as x approaches 2. Okay. So I could just plug it into here. So that value is going to be 2 plus 1. That's also equal to 3. So it's approaching 3 at x equals 2, and the value of the function is 3 at x equals 2. So the fact that the limit and the actual value of the function at x equals 2 is the same, that tells us that h of x is continuous. At x equals 2. So we did a little trick by putting an extra little condition or piece of the function that would have caused a problem, which it did in part B. Now, if you wanted to check if it was continuous at any other point, just like the first function, again, it would have been continuous anyways, even without this patch. Okay, so here we have another rational function. This time we have 1 on the top over x minus 2 squared. And again, we're checking for, is it continuous at x equals 2? So as soon as we plug in, this is capital F of x, sorry, we want to plug in capital F of 2, you can see again we're going to get 1 over 0, okay, because we get a 0 squared on the bottom, and this is undefined. This would actually be a vertical asymptote, and since the value of the function at that x equals 2 is undefined, again, just like in B, we don't have to go any farther, because if that value of the function does not exist, then it's not continuous. We don't have to check the limit at all. So therefore, f of x is not continuous at x equals 2. And if you remember from your advanced functions, that's actually going to be a vertical asymptote, which is one of the 3 reasons for a function being discontinuous. So we got a hole in B, we have vertical asymptote in D. Let's see what we have here. So this is our last example. We have a piecewise function. Again, not a bad idea to do a little sketch. Okay, and we're looking at x equals 2. That's where something interesting is going to happen. So basically if x is equal to or greater than 2, so beyond this point, so it's always going to be, the function is always going to have a value of 3 when x is greater than or equal to 2. So that's one piece of the function there. Okay, and if I was to look at the other side, if I plug in, if I just see where the limit of this function would be, if I plugged in a 2 here, I get 4 minus 0, sorry, 4 minus 4, which would be 0. Okay, so what does this look like? This would be so we have an open circle here, and it'd be at 0 the value would be 4. So it's basically a parabola that opens like that, 4 minus x squared. That should be looking more like an open circle. Open circle here, closed circle here, and you can see right away that this at x equals 2, g of x is not, the limit does not exist. Okay, so looking at the two sides, limit as x approaches 2 from the negative side of g of x. So from the left side, the actual value is 0. And from the right side of 2, as x approaches 2 from the positive side, g of x, that limit would be 3. Okay, so you can see right away, the limit does not exist as x approaches, well, I'll just make it a little more vague. The limit does not exist, and since the limit does not exist, g of x is not continuous there. At x equals 2. Okay, now from the graph you can see that's the third example. This is where we have a jump. So basically if I'm drawing my graph, I get just before the 2, then I have to lift my pencil and jump to a different value to continue. Okay, so the reason for this would be a jump. Discontinuous due to a jump. Okay, so you can see this is just kind of a level above whether or not the limit exists. If the limit exists, then you can test to see if it's continuous as well. It may or may not be if the limit exists. You see in different cases. So if I go back to first page, just to try to keep things clear in your mind. So in this example, the limit exists. The limit at x equals 1 is, as x approaches positive 1 is positive infinity, but even though the limit exists, this is not continuous, okay, because there is no value of the function at x equals 1. Here, this is one we just did, really. We have a piecewise function. The limit does not exist here because the limit from the left side is not the same as the limit from the right side. So if that's true, limit doesn't exist, it has to be discontinuous. We don't even care what the value of the function is, because if the limit doesn't exist, it doesn't matter. Okay, here's a function that the limit exists also, but there's a hole there, and that was the other type of being discontinuous even if the limit exists. Okay, so hopefully that makes sense. There's some homework, page 52 at the bottom of the page. Just try a few of those, make sure you get the feeling for how this works. And so this is the third lesson of the week. We will do an assignment that I'll be posting Friday at 3. It'll be primarily focused on the last 3 lessons that we did this week, 7, 8, and 9. Obviously, though, you do have to have some knowledge of the previous lessons, as these lessons kind of built on each other. Okay, so don't forget we have my office hours tomorrow, Thursday, or actually today by the time you listen to this, Thursday 1 o'clock to 3 o'clock. If you have any questions on this or any of the previous lessons, feel free to ask. Okay, so hope to hear from you soon, and good luck on the assignment, and we'll see you on the next lesson.